Okay, so I have written up here at the top a summary of what you should now know. So the definition of what momentum is, it's mass times the speed of an object. We learned that Newton's second law can be rewritten in terms of momentum to say that a force causes the momentum of a system to change. And then we learned that if there was no outside force acting on the system, then the momentum you begin with has to equal the momentum that you end with. Now we're going to apply that to an explosion, but don't get your hopes up, it's not that big of an explosion. So we're going to click on the physics classroom, and I wanted to show you all the different features of this website here. So when you click on it, you're going to come to here, and then notice that you can do tutorials over different aspects of physics. You can watch simulations, which is what we're going to do. You also have videos that illustrate concepts. There's stuff about chemistry, and then Concept Builders down here has questions that you can answer over this stuff. And then there's even more stuff underneath it. So I will let you take a look at this if you want to. But the main thing is that we want to look at the simulations. So let's click on simulations. And then here's all the different kinds of simulations. So this first one here would be simulations about what do we mean by distance, speed, and acceleration. We've already looked at a simulation for Newton's laws of motion. They got vectors and projectiles, forces in 2 dimensions, but this is the one that we want, momentum and collisions. Okay, now we want to know which simulation on momentum and collisions. So we're going to go down to here, and it's going to be this one. So collision carts, and then we need to launch the interactive. So now we're down to here. Okay, so now the question is, what kind of interaction do we want? So we have the elastic collision, the inelastic collision, and then the explosion. So we're going to click on the explosion. So if I click on it, you see that we start with 2 cars that are connected, and then when I hit the go button, the start button up here, there's going to be an explosion that's going to cause the 2 carts to move away from each other. Now you might be saying, how does this go with conservation of momentum? Because I said that the force has to equal 0 in order to have conservation of momentum. And you would be saying, but yeah, if I click the start button here, there was definitely a force because that force pushed them apart. So if there's a force, how can momentum be conserved? Well, this is an outside force acting on the system, whereas the force in that was an internal force that caused the 2 to separate. So if you were to draw a circle around the 2 cars when they're put together, so the 2 cars represent the system, and so there is no outside force acting on the system. There's an internal but not an external. So we can use conservation of momentum in order to do that. I hope you got that. Now we can change the initial velocity, so we need to reset it. Okay, and we can change the initial velocity of the system by moving these things here. Now did you notice that when this one changed, this one over here changed? And so that's because they're hooked together initially. Okay, then we could also change the mass of the carts if we want. Okay, and then we could hit the start button, and then it's going to tell you the final speeds of the cards. Do you notice this one's a negative? So what does a negative velocity mean? It's moving in that direction. Okay, so let's go back to the lab here. Go back to the lab. Go back to the lab. Oh. Nothing like a smooth lecture. So now we're down to here. Okay, and now we're going to make use of this conservation of momentum. The momentum that you start with has to equal the momentum that you end with. So what was the initial momentum of the system? So when they were stuck together, you had the total mass of the two cars when they were stuck together. So that would be M1 plus M2. And then you had the initial speed of the two cars when they were stuck together. So I could even put an I for initial there. Okay, then that's going to equal, now it's blown apart into two pieces, so now we have to have two momentums. We're going to have the momentum, so the M for the red car, times the speed of the red car final, plus the mass of the blue car, and then the final speed of the blue car. So that's conservation of momentum for an explosion. Okay, now you're going to be filling in this chart down here. So I'm going to give you the initial mass of the red car. I'm going to give you the initial mass of the blue car, and I'm going to give you the initial velocity of the before the explosion occurs. Now you have to figure out what's the initial momentum. Okay, so to find the initial momentum, you're going to need to do this part right here. So you have to find the total mass and multiply it by the initial speed, the initial velocity, which is going to be pretty easy. And then you're going to put that number right there. Okay, then you're going to hit the go button. Okay, so if we go back to the simulation here, and so it's over with, so we need to reset it. Okay, then you need to change the masses, you need to change the speed here, and then you need to click the go, and then you're going to take these two numbers, now they're going to be different numbers, and then those two numbers are going to go here and here, and then you can also calculate the final momentums, because you're going to take the final speed and multiply it by the mass of the red one, and then that goes here, and then you're going to take the final speed of the blue one, and you're going to multiply it by its mass, and it's going to go right here, and then you're going to add those two numbers together so that you get this one down here, the sum of the momentums. So how do you think that this number over here should compare to this number over here if momentum is conserved? Well, I'll let you do the experiment and then answer this question number one, and then was momentum conserved? Now, unfortunately, the simulation only goes to like two significant figures, so sometimes it may not exactly be the same. So this number should be the same as this number here. Oh, I just gave it away. But if they're not the same, it probably means that there's a slight error in the significant figure thing. So don't worry about that. Okay, now we're going to reset the simulation. Didn't want to do that. now we're going to reset the simulation, and here's your initial values of 2 and 3 and an initial velocity of 0. And this time you are only, and you hit the go button, only look at the red car. Don't look at the blue car, okay? Just look at what the red car does. And then put right here what its final velocity is. Okay, so I'll go ahead and do one for you just so that you can see what's going on here. So the initial mass is going to be 2 for the red and 3 for the blue. So it's going to be 2 plus 3. And then the initial speed was 0. And then that's going to be equal to, okay, now the mass of the red one was the 2. And we're going to get its final velocity from the simulation. So let's go ahead and put the simulation back up. So we need the red one to be a 2, okay, and then we need the blue one to be a 3, so that's good, okay, and then we need the velocity to be 0. Oh, need to reset it. Okay, so this didn't change, that didn't change. Okay, now we're going to put this back on 0. So the initial velocity was 0. Okay, now we're going to start it. And we get a -5 and a 3.3. But don't look at the blue one. We're only interested in the red one. So the red one is going to be -5. -5. And then plus, let's go ahead and put in the mass of the blue one, which is going to be 3. And then I'm just going to put a V. That's what we're trying to solve for. So we know all this other information, and we're going to solve it for the letter V. Well, this is 5 times 0 is 0. And then that's going to be equal to -10 plus 3 times V. Okay, then take this over to the other side. And now you got 10 is equal to 3V. And then take the 3 over to the other side. And then you're going to finally end up with that the final, let's go ahead and put final velocity of the blue car. So final B is going to be equal to 10 divided by 3, and then that's going to be meters per second. So I'm going to let you do that, and you will get a number, and then what I want you to do is to compare that number to this number right here. And it may not turn out to be exactly correct. Okay, so you're going to have the final velocity of the blue car, and then the final velocity from the simulation, and then hopefully these two numbers are going to be the same. Okay, now you're going to do it again, but it's going to be a little bit more difficult this time. So notice that we've got the same two masses, but the initial velocity is different. So it's not 0, okay, but you're going to do it exactly the same way. Put all your numbers into this formula, solve it for the final velocity of the blue car, put that number down here, and then look at the simulation and see if you got it right. Got it? Okay. So that's part 2, and let's take a break, and when we come back, we're going to do part 3.